Hello, everyone. This is Quan Wang from Google. Today, I will be talking about on the success and the limitations of auxiliary network-based word-level end-to-end neural speaker diarization. A very high-level overview of this work. The problem we are trying to solve is we want to add speaker diarization capability to any off-the-shelf transducer-based ASR model, and there should be zero word error rate regression. Also, we want to get rid of any speaker embedding or clustering. As we know, speaker embeddings are often considered as biometrics, which is challenging to work with, and clustering is usually unsupervised. Our proposed approach is called word-level end-to-end neural speaker diarization, or WEEND. We add auxiliary encoder and joint network to a frozen ASR model, while we share the blank logits with ASR. With this approach, we see performance gains on two-speaker and short-form cases, but the initial results are not good on multi-speaker and long-form cases. Our ablation study shows to really make this approach work, we need more balanced data, increased sequence length during training, and post-processing systems like DiarizationLM. So here is today's agenda. We will start with motivation. So let's think about deploying a speaker diarization system. Assume that we already have a pretty good speaker diarization system. It can be based on any mature algorithm, like clustering D-vectors, permutation invariant training, or target speaker VAD. Doesn't matter which one it is. Assume we get pretty good diarization error rate on the evaluation datasets, and now it's time to put it in production. The first challenge is that we need to combine it with ASR. All the speaker diarization systems shown from previous slide, they answer the question, who spoke when, giving you timestamps for each speaker. But in most realistic applications, we need who spoke what. So how do we do this? The most common approach is just to compare the timestamps between the ASR system and the diarization system, and assign a speaker label to each word recognized by ASR. And this can be very problematic, because the two systems are usually trained with different datasets and algorithms. The timestamp of each system can be very inaccurate. And when you combine them, you get lots of errors. Looking at this example, ideally, the timestamps of speaker 1 will overlap with the timestamps of good morning, while the timestamps of speaker 2 will overlap with the timestamps of how are you. But in reality, a very small time misalignment can result in big differences. A common solution to this problem is to train ASR and speaker diarization jointly, such that we no longer need to rely on timestamps. And there are many existing work in this direction, which I will briefly review here. Most of such work are based on RNN transducer or transformer transducer, which are the mainstream frameworks for end-to-end speech recognition in recent years. RNNT and TT allow us to introduce new task-specific tokens to the output vocabulary. I will show some examples next. One of the earliest work is for medical speaker diarization from Google. In this work, the authors introduced the two tokens for the role in the conversation, a token for the doctor and a token for the patient. This is a good start, but it's not solving the real problem, because speaker labels must be permutation invariant. Another work from Google is turn-to-diarize. This work introduces a single token ST to represent a speaker turn. Then speaker embeddings are extracted from each turn and being clustered. There is also the speaker attributed ASR system by Microsoft. It's very close to what we want to achieve here, a speaker label for each word, but this system still relies on speaker profiles as input, which is something we want to avoid here. Another similar work is called target speaker ASR. This approach requires the target speaker embedding as input, then we'll diarize each target speaker. So let's assume we have a jointly trained ASR and speaker diarization model, such as the SAASR or TSASR system introduced earlier, ideally, we just show that this model has great speaker derivation performance on some of the evaluation datasets, and we deploy it. But in reality, because this is a joint ASR and speaker derivation model, we have to compare its word error rate with the best ASR model as the baseline. And because we are adding new capability to the model, there is usually always some regression on the ASR performance, which can be a notch blocker. So why do we have this performance gap between the best ASR model and the joint ASR and speaker derivation model? There are many reasons. For example, there are much more ASR training data than diarization. The algorithm that works best for diarization may not be the best for ASR, and the two systems can be owned by different teams with different priorities. So we believe it's much easier if we can add speaker diarization capability to any off-the-shelf transducer-based ASR model without any word error rate regression. And I will talk about our system next. So this is a high-level system diagram of our framework, word-level end-to-end neural diarization. Given a production-ready ASR model, we freeze all its components, including the encoder, the decoder, and the joint network. Then we introduce two auxiliary networks for diarization, an aux encoder and an aux joint network. The aux joint network we introduced here will output a sequence of integer speaker labels. And for the joint network, we share the blank logits with the ASR joint network. This is a very important trick, because with this trick, we can make sure that the two joint networks will always produce sequences with exactly the same length. That means one speaker label for each ASR word. With this new framework, we train it only on speaker diarization data and optimize the RNNT loss on the sequence of speaker labels. And the best part here is that because we freeze all ASR components, the ASR output will be exactly the same with the original model. That means there is zero regression on word error rate, while we have this new speaker diarization capability in this model. So next, I will talk about the experiments. For the datasets, we use both standard public datasets for speaker diarization, including AMI, Cohom, and Fisher. We also generated simulated dataset to augment our training and evaluation data. We simply concatenate utterances from Interspeech with inserted pause and cross-fading for 2 to 4 speakers. For the baseline model, we use the turn-to-diarize system with a multi-stage clustering. This baseline model uses a global configuration for all evaluation datasets and has near state-of-the-art performance on all the evaluation datasets. We report two metrics. For ASR, we just use word error rate. For speaker diarization, we use word diarization error rate, which is calculated on the correct and substitution words only. The ASR model we use is a pretty simple transducer model, conformer encoder, embedding-based decoder, and a linear joint network. Nothing fancy here. On top of the pre-trained ASR model, we add aux encoder and aux joint network to it. The aux encoder collects to the 5th layer of the ASR encoder and has 9 LSTM layers. The aux joint network is just a DNN, and the output vocabulary is 8 predefined speaker tokens. This means we support at most 8 output speakers. During training, we need to train on batches efficiently, so we segment all of our training data into chunks of 15, 30, and 60 seconds. We only train a single model on the mixture of all training datasets and evaluate it on all testing sets. I will show the experimental results next. When we take a first look at the results here, on the Cohom evaluation dataset, we see the word diarization error rate of the proposed model is much better than the baseline, but it's much worse on Fisher and AMI evaluation datasets. On simulated data, the result is also quite mixed. It's better on 2 or 3 speakers, but worse on 4 speakers. So our initial observation is that the sequence length is a huge challenge here. During training, we need a max sequence length to build batches, such that we can train efficiently. And the max length is 60 seconds in our training setup. But for an utterance in the AMI eval set, it can be 30 minutes long. This is a huge mismatch between training and evaluation, and we are losing the cross-chunk context here, which is very important for speaker diarization tasks. To investigate this, we created another version of the evaluation dataset, such that the maximum length of an utterance is at most 120 seconds. On these segmented datasets, now we see the proposed model is better than the baseline model on both Coulomb and Fisher, and on all length variants. So this is great. However, on the AMI evaluation dataset, even if the data has been segmented, the proposed model is still worse than the baseline. So we keep asking why? Why do we see this? So our next study is to break down AMI evaluation dataset by number of speakers. And now we see a clear pattern that the proposed approach is better than the baseline system only for 30 or 60 seconds, and only when there are at most 2 speakers. So why do we have these limitations? For sequence length, we have already discussed that. The performance will be poor on utterances that are longer than sequence length of training batch, which is very expected. Another limitation is the poor performance when there are more than 2 speakers. This is because we only trained a single model on the mixture of all training data, and these training data are extremely unbalanced. AMI is the only training set that has more than 2 speakers, and it is extremely small compared with Fisher. To prove our explanation, we did some more ablation study on the simulated data and segmented data. If we remove the simulated data, we are going to see a big performance drop on all evaluation datasets. Because our simulated data have a better balance for utterances with more than 2 speakers, so as expected, AMI has the biggest performance drop. We also tried to further remove the 30 and 60-second segments from the training, and only use 15 seconds, and this gives us even worse results. And this is very much expected, as we are making the sequence length mismatch even bigger here. Another ablation study we did is where is the best place to hook the aux encoder to. We experimented with 3 variants: the input layer, the middle layer, and the last layer. And the best result is from the middle layer. This is also very expected. For speaker diarization, we need both acoustic and semantic hints. The input layer only has the acoustic hints, and the last layer only has the semantic hints. So we don't expect them to work as good as the middle layer. Let's get to the conclusion and the future work. So we proposed word-level end-to-end neural diarization in this work. It allows us to add speaker diarization capability to any off-the-shelf transducer-based ASR model. We can get rid of speaker embedding and clustering. There's 0 regression on ASR, and it outperforms the baseline model on short-form and 2-speaker cases. These are the successes. The proposed approach, however, with its current setup, has limitations. The performance is bad on long-form utterances due to training constraints. The performance is also bad on utterances with more than 2 speakers due to unbalanced data. But we can look at the bright side because all the limitations are only transient. If we look at the recent advances of large language models, we know that training with much longer sequences is possible. We just need better GPU or TPU. And the data issue will also ultimately be gone. This research is constrained on only using public datasets, which are extremely unbalanced, but there are tons of data available in the wild for future uses. And also, there's DiarizationLM, which can be used as a post-processing step of any ASR and diarization systems. If you are interested in this work, please come to our poster session on Wednesday. And that's the end of this presentation. Thanks for listening. We have some time for questions.